So in the last slide, there was a little bit of information on a half-life, and half-life is actually another really important concept when it comes to the different rate laws you can see. So let's talk about what half-life is first of all. Half-life is literally a time, so it'll be a value in seconds, minutes, hours, something like that, and it's the time it takes for half of a sample to disappear. So that means that half of the sample has reacted, if you will, and half of it is left. And for first order reactions especially, half-life is very, very helpful. So on the graph there on the right hand side, we're talking about hydrogen peroxide, H2O2, and we're starting at 0.020 moles per liter at the top. And you can see what they're doing. They're plotting then the amount of time, which is the x-axis, the amount of time it takes to go to one half-life. What that means is the concentration goes from 0.020 to 0.010. Then it takes another half-life to go half of that value, so to go from 0.010 to 0.0050, etc. And the half-life should be the same. So half-life is really an interesting idea. What's important to realize is that one half-life, you're down to half the sample. It's not two half-lives to get to zero sample. Two half-lives would be half of the half you were left with, or 1/4 of the original amount. And another half-life would be 1/8, 1/16, stuff like that. So it's kind of crazy. In theory, you never get to zero, all right? And that's a little disturbing. If you have something radioactive, you're going to have less and less and less and less and less, but will you get down to zero? Probably not. But half-life does have a lot of cool uses, and we'll talk more about this as we go through this section. Hydrogen peroxide has a half-life of 654 minutes. So if you start again with a 0.0200 molar solution, in one half-life, or 654 minutes, you'll be half of the reactant remaining. So you'll be down to 0.0100 molar. After two half-lives, that doesn't go to zero, you'll be half of the 0.01 number, you'll be down to 0.0050 molar. And after another half-life, then you're down to 0.0025. So you can see how you went from 0.02 to 0.0025 there in just three half-lives. However, it's not to zero, and that's what's really important. So we would say the half-life for hydrogen peroxide is 654 minutes. And you could convert this to seconds if you want. You could multiply by 60 seconds per minute to get the half-life in seconds. You could also convert it to hours. You could divide 654 minutes by 60 minutes per hour to get hours. Any kind of units are fine, and you can adjust them as you need them. Half-life gets that symbol T1/2, so if you see that, that's what it's referring to. Sugar, like most biological processes, is a first-order process when it ferments, and sugar and the enzyme make some kind of products. And the rate of disappearance of the sugar, it's a first order, rate equals K times the concentration of the sugar to the first power. And rate constant K, 3.3 times 10 to the minus 4 inverse seconds. So the question is here, what's the half-life of this reaction? And this is kind of a problem you might run into. Now, to answer this, what we're going to do is we're going to go back to the first order integrated rate law, where natural log of R over R0 equals minus KT. However, before we do that, R over R0 is going to equal 1/2 when we're at half-life. So if you started with 5 moles, you'll be down to 2.5 moles. If you started with 1 mole, you'll be at half a mole. But whatever you start with, R0, R will be half of that number when you get to the half-life. So R over R0 equals 1/2 when the time equals half-life, T1/2. So if you rewrite natural log R over R0 as natural log 1/2, that equals minus KT, but T at this point is the half-life, T1/2. So you can see what's happening here. We've got natural log of 1/2 essentially equals minus K times T half-life. Now, natural log of 1/2 is minus 0.693 in your calculator. So minus 0.693 equals minus K times T1/2. And if you clean that expression up, half-life, T1/2, equals 0.693 divided by K. K. And this is pretty cool for chemists. So in this problem, the K value, 3.3 times 10 to the minus 4, we can find the half-life easily. 0.693 divided by the K value, 2100 seconds. And if you divide that by 60 seconds per minute, you'll get 35 minutes. So anyway, a couple of things about half-life. Half-life is time. All right, just like rate constant, it's going to be a positive value. You have to have the same units for K and half-life. So in this problem, K was in inverse seconds. That means half-life will be in regular seconds. All right, if the K would have been inverse minutes, half-life would have come out to be minutes, stuff like that. So here's another problem. For a given first-order reaction, K equals 0.347 inverse hour, what's the half-life of this reaction? So K equals 0.693 divided by half-life, or half-life will be 0.693 divided by the 0.347 K value. But the value you get initially is going to be in hours, because remember, K and T have the same kinds of units. So the half-life you initially calculate will be in hours. All of those answers are in minutes, so we have to convert then hours to minutes. So in this problem, once you convert half-life, 0.693 divided by 0.347, the answer comes out to be hours, and you need to multiply the hours by 60 minutes per hour to make sense with the answers you're given. So if you do all of that, it comes out to be 120 minutes, and we're good to go. Now, personal apology, I used to play a game called Half-Life a lot, and in Half-Life, there was a character, Dr. Gordon Freeman, and this is the last answer there on E, and that little blurb right there is just a memoir of all the good times I spent in that game. But anyway, that's really nothing you need to worry about. It has nothing to do with what we're talking about. But when I think about Half-Life, all right, I think about this game. Yes, I need therapy, I know. But anyway, hopefully you understand half-life, K values, blah, blah, blah. Here's another kind of question you might run into. We've got the same kind of problem, got the sugar, got the K value, 3.3 times 10 to the minus 4, half-life, 35 minutes. We just calculated. We're starting with 10 grams of sugar. How much is left after 2 hours and 20 minutes? Okay? And this is a kind of problem that can be answered in two different methods. I'm going to talk about one method, which is the Chem 104 method, and I'm going to talk about the better way, which is what I'm going to call the Chem 222 method, okay? Now, in Chem 104 and the lower chemistry classes, how we would answer that is we'd figure out how many half-lives elapsed in 2 hours and 20 minutes. So because an hour is 60 minutes, so 2 hours would be 120 minutes plus 20 minutes, 140 minutes total. And the half-life, as we saw in the last problem there, 35 minutes. So the total time divided by the half-life time gives you the number of half-lives, 4 half-lives in the Chem 104 method. So what you can do, if you're starting with 10 grams, after the first half-life, you'll be at half that, 5 grams. Second half-life, 2.5, 3, 1.25. Fourth half-life, you'd be down to 0.625 grams. And that way does work, especially if you have an integral whole number of half-lives that have elapsed. But a much, much, much better way to do this is to use the first-order integrated rate law. Now, a couple of things about this. K is in inverse seconds, and we have hours and minutes. So you have to convert hours and minutes into the same kind of units as K. So 140 minutes, which is what we saw earlier, times 60 seconds per minute, that's going to give you 8,400 seconds. That's going to be the T value here. And we know that R0, how much we start with, is 10 grams. We have the K value. We just calculated T. So the only thing here we don't have then is R, how much is left. So if you go through the math, natural log of R over 10 equals minus KT. And then you have natural log of R over 10 equals minus 2.772 when you multiply those together. Now you need to use the anti-natural log. That's the little e to the x button we've talked about earlier. That gets rid of the log on the left side, and e to the minus 2.772 is 0.0625. So if you multiply that by 10, that's going to give you the amount left after this long, 0.625 grams. Now, why I like this method better and why I encourage you to use this is you can have any number of half-lives. It doesn't have to be a whole number, and you can automatically calculate calculate how much is left. Now, you do have to use anti-logs. I understand that's not a lot of fun sometimes, but it's all stuff you can do. Let your calculator do the hard work, and you are good to go. So I do recommend using the Chem 222 method, quote unquote. You're not limited to the whole number of half-lives. It's pretty chill. Again, that e to the x, that e is just a constant. It's called Euler's number, 2.71828. It goes on for a long time like pi. Nothing you have to do. Let the calculator do this work and you will be good to go. As I stated earlier, all radioactive processes, as well as all biological processes, as far as I know, follow first-order kinetics. So first-order kinetics and this first-order integrated rate law and half-life become super important when it comes to radioactive decay, which we'll talk about more in the next chapter. So here's an example of this. You can have tritium, which is a radioactive isotope of hydrogen, decompose into an electron and a helium-3 nucleus. And if you start with 1.50 milligrams of tritium, how much tritium would you have left after 49.2 years? And the half-life for this process is 12.3 years. We'll talk about this kind of reaction in a future lecture. What I would do here, I would use, once again, you know it, the first order integrated rate law. Now, we don't know R, how much is left, but we know that R0 is what we start with, 1.50 milligrams, and we want to know T, how much is left after 49.2 years. But we don't have K. So right now we have one equation with two unknowns, R, how much is left after that long, and we don't have K. However, the half-life allows you to find the K value pretty easy. K equals 0.693 divided by the half-life, and if you do that, that's 0.0564 inverse years. Now again, make sure that your K value, your half-life, and the time elapsed are all the same kind of units. So in this case, we're using all years. You wouldn't want to use years and months and days or something like that. They all have to be the same kind. K will be inverse time, but it still has to be the same kind of unit. So anyway, natural log R over R0 equals minus KT. We've got all the pieces we need now. The minus KT part comes out to be minus 2.77. You can do the anti-log of that to get rid of that. That's the Euler's number once again. Make sure you know how to do this, 0.0627. And if R0 was 1.50 milligrams, then R is 1.50 times 0.0627, we have 0.0941 milligrams left. And this is kind of cool because who wants to wait 49.2 years for something to happen? Not me. I can't even wait in line at the store. But anyway, that's a personal problem. Anyway, this is a quick way then to find the time elapsed without having to actually be there, which is really powerful. And in terms of our human lifetimes, some of these times elapsed will be huge amounts of time. You couldn't wait, but we can calculate it because we've modeled it with physics and math and chemistry. Oh yeah. In this problem, we have a copper-64 isotope, which is radioactive. Apparently, it's used in studying Wilson's disease. Anyway, the half-life here, 12.70 hours. What fraction of copper-2 acetate remains after 2.0 days? Fraction problems with radioactivity means what's R over R0? All right, that's kind of what it's trying to ask for here. And we have here a half-life. We have here a time elapsed. So natural log R over R0, which is what we're trying to solve for, equals minus KT. We don't have K, but we have a half-life. So we'll turn the half-life into K. K times T, natural log R over R0 equals minus KT. We can go from there. So if you do the math, 0.693 divided by 12.70, the half-life, that's going to give you the K. I didn't even calculate it in this problem. I just threw it in the problem and multiplied it by 48 hours, which is 2 days, by the way. I forgot to say that, but remember, all these things have to be the same time system. So R over R0 will be the anti-natural log, e to the power of minus 2.6192. We're going to have a fraction left, 0.073. So kind of cool to figure these things out. Half-lives for radioactive substances are all over the spectrum in terms of time. Uranium-238 has a half-life of 4.5 times 10 to the 9th years. So 10 to the 9th is a billion. That's going to be 4.5 billion years. And of course, nobody's sticking around that long to measure that. So thank you, science and math, for letting us do this. Carbon-14 is actually pretty helpful to scientists. Carbon-14 has a half-life of 5 5,730 years. And then you can see iodine 131's half-life. That was released into the air around Hanford in eastern Washington back a couple decades ago. Not the best. Element 106 is one of the newest elements. It's seaborgium. Seaborgium has a very small half-life, 0.8 seconds. So imagine you have 1 gram and you want to show a friend. Well, basically 1 second later, you're down to half of your sample, which probably wasn't real big to begin with. Crazy, crazy. But element 111, Roentgenium, named after the X-ray scientist, has a half-life of 0.0015 seconds. So very, very small. So anyway, just realize half-life is a powerful concept. Half-lives can be super long, super short. Wow. Half-life of caffeine is something that I find personally relevant because I drink way too much coffee, but that's not my problem. They claim the half-life of caffeine in our body, 3.5 hours. So that means if you consume some caffeine, 3.5 hours later, you're down to half the caffeine. Another 3.5 hours, you're down to half of the half, et cetera, et cetera. Medicine is also a field that uses half-life as well. You can have half-lives for other types of expressions. We're mostly focusing on first order here, where half-life is 0.693 divided by K, and that's by far the most useful. If you ever do a second order half-life, you have to take into account the initial concentration, A0, and that's another thing we won't talk about here, but it is something that can be calculated. Zero order also has a concentration dependence on the initial amount you start with. So anyway, first order, it's especially useful to have half-life values because it allows you to find K directly. When you have second and zero orders, you need to know the initial amounts. Not quite as handy, but it can be cool.